This YouTube video is a summary of a couple of days of class for Mr. Spencer's Honors Physical Science class. We start our investigations of force and motion with several one-dimensional motions. And in order to determine things that we can measure in one-dimensional motion, we need to be able to use a coordinate axis system for reference. A coordinate axis system has three basic components. It has an origin, it has a unit of measurement for increments, and it has direction. The students in my class help collect data for two cars, a blue car and a red car. And here you see the data that was collected. I have a picture here of a number line, and it has the three components of the coordinate axis system that we just talked about. It has an origin, it has a unit of measurement, and we use the tiles in the hallway, which are 1 foot long, as our unit of measurement. And it also has a direction. We call to the right on this diagram positive, and so to the left would be negative. And one of the things that you'll notice when you look at the data tables is that as time progressed for the blue car, the position went positive or in the positive direction, and the red car went in the negative direction. Here is a dot that represents the starting position for the blue car and the arrow that represents the direction that it traveled. And here is a dot that represents the starting position for the red car and the direction of its travel. Once data is collected, the next thing that we want to do is to plot this data on a graph and try and analyze it. We decided to plot the data sets for the blue car and the red car on an application that could be used for with the Chromebook called Desmos. It's an app that can be installed with the Chromebook. It's also an application that just can be used with a regular desktop. If one goes to or does a Google search for Desmos and selects calculator, then one can begin the process of plotting the data. So you see, here is the data set for the blue car, here is the data set for the red car. And these data sets are plotted on a position versus clock reading or time graph. And the first thing that you should recognize is that both data sets, the blue car data set and the red car data set, produce straight lines. When you have straight lines, you can calculate the slope. So we should analyze the slope of the blue car and the red car a little bit further to see if we can come to some understanding of what the slope means. In addition, you see the values for the vertical intercept for the blue car is 1 and for the red car is 4. This corresponds exactly to their starting positions. And in fact, that's what the vertical intercept on a position versus time graph means. This is the initial position of the red car, and this is the initial position of the blue car. Another cool thing that Desmos does is that it will generate a best fit line that you can see already graphed through the data set for both the blue car and the red car, as well as the statistics for that best fit line. And so the blue car, according to Desmos, has a slope value of 1.49 and an intercept value of 0.985, while the red car has a slope value of negative 0.498 and an intercept value of 4. Now we've already discussed that the vertical intercept of the blue car is its starting position, and you can see the very close comparison between the value of the best fit line vertical intercept 0.985 and the actual value of 1 for the starting position of the blue car. Likewise, the red car has exactly the same starting position from the best fit line as what we know it to be from the experiment. So here is the position versus time graph of the blue car that I graphed on a different computer program called Locker Pro. You still see the intercept value, you still see the positive slope. But what I wanted to highlight on this particular graph was the labels for the vertical axis, which is X, which represents the position in feet. And along the horizontal axis, the label is T, which represents time or clock reading in seconds. And if we were going to calculate the slope of this particular linear graph, then we would, as we have learned in math, calculate the rise divided by the run, or rise over run. To put meaning to the rise over run of this graph, it makes sense to analyze the units of rise over run. And so if we were to calculate a rise, we would be looking at a change in feet. And if we were looking at the run part of the calculation of the slope, then we would be looking at a time interval measured in seconds. Here is the same picture with the best fit line drawn on the graph and the data points selected to calculate the slope. And as you've probably done in math class, calculating the rise over the run for these two data points will generate the slope. If we look specifically at what the rise means, then you could see that the values used in the rise will both be position values. Specifically, this change in position will be the final position minus the initial position. And that delta or triangle X means literally change in position. Looking at the run calculation, which is really this time interval here, in order to calculate it, we would need to know what the value of the final time or clock reading is and subtract the initial clock reading from that value. So analyzing our slope units, it comes out to be feet per second. Now, what kind of a quantity would feet per second describe? If you think about the units feet per second, it sounds an awful lot like miles per hour. And so we might think that the slope represents the speed. But if you'll recall, our red car had a negative slope, and you don't ever describe things as having negative speed. So a similar term, velocity, is what we define our slope of the position versus time graph to be. So here are a couple of definitions that we get from our analysis of the linear position versus time graph for the blue car and the red car. In calculating the slope, we determined that the rise was a position change and the run was a time interval. And so we define the slope to be the velocity. And we use the term velocity as opposed to speed because we noticed that our red car had a negative slope. And so velocities can be negative, but speeds cannot. The rise quantity, this change in position, is also known as the displacement. And again, this triangle symbol literally means change in. And to calculate delta x, we would be finding the final value of x minus the initial value of x. Distance is a quantity that is similar to displacement, and it often has the same value, means the same thing. But distances are always positive values and simply answer the question, how far? Whereas displacements are more formally defined as a position change and can be negative. Let's revisit the graphs of the blue car's motion and the red car's motion plotted again on the same graph of position versus time. Here I've labeled the slope of the blue car, which is about 1.5 feet per second. And here I've written down the slope of the red car, which is about negative 0.5 feet per second. So I guess the question is, which car is faster? Well, if you think about how quickly the position changes for the blue car compared to how quickly the position changes for the red car, then you would come to the conclusion that the blue car's position changes more rapidly than the red car. So we would say that the blue car is faster than the red car. Now, how might speed be identified on a position versus time graph then? If you didn't have the numbers written down, could you still determine which car was faster? And the answer is quite simple. Yes. Whichever has the steeper slope on a position versus time graph will be the faster object.